All right, this is AP, AB, and BC calculus. We're doing the area between curves expressed as functions of x. So in this video, we'll talk about functions of x. In 8.5, we'll talk about functions of y. So to calculate the area between two curves, specifically ones that are functions of x, we integrate the top curve minus the bottom curve. So by top curve, I literally mean the curve that is physically higher, so the one that is blue in this particular picture. And by bottom, I mean the one that is physically lower, so the one that is red in this picture. So this green area would be the integral from a to b of the top curve, f of x in blue, minus the bottom curve, g of x in red, dx, right? So on a calculator section, it doesn't actually matter which of the curves is on top because you can totally cheat, and instead of figuring out which curve is on top, you could just integrate the absolute value of the difference. You could either do f minus g or g minus f, and you could integrate the absolute value of that difference, and that would work just fine. So good to know, right? Cool. So moving forward, let's talk about why this makes sense. So why does this make sense? Well, I've given you two graphs, and f of x equals negative x squared plus 2x plus 4, which I graphed in red here. That's the parabola that you see 3 times. And g of x equals negative x plus 4, which is this black line that I graphed. So if you were to integrate just f of x, like integrate just f of x from 0 to 3, you'd get this blue shaded area. If you were to integrate just g of x from 0 to 3, you'd get this yellow shaded area. Well, you can see that if you took the blue area and subtracted the yellow area, the spot you'd get is the green area, which is the area between the two curves. So that's why it works the way it does. It wouldn't be wrong to do it like this, where you integrate this whole thing, get a number, integrate this whole thing, get a number, and then subtract them. That's fine. It's just a little bit easier to recognize that you can do a single integral. So non-calculator, let's find the area between the two curves on the interval from 0 to 5. So it is worth noting that it's kind of helpful to picture what this graph looks like, right? So you don't have to do this, but I'm going to argue that it's easier if you can graph what these intersections are. So if you graph where they intersect, it's going to make your life a lot easier. So if you say, where does f equal g, right? And if you move stuff over to solve, you'll subtract this over, you'd get x squared. So you subtract the 9 over, it's gone. You add the x over, so x squared minus 5x equals 0. You're going to get that this thing intersects at 0 and at 5, right? So x is 0 and x is 5, which fits with the bounds I gave you anyway, right? And if you were to graph this, you don't have to do a great job graphing it, but here's what you know. You know that this is a line that has a negative slope, right? And you know that this is a smile. So essentially what we're looking at is a graph that looks something like this, right? And I know that the smile has to be on the bottom, because if you picture a line that looks like this and a smile, the only way they intersect is if the smile's on the bottom, right? Because if it looked like this, they would not intersect, right? So it has to look like this. So my top curve is g, my bottom curve is f. So I want to integrate from 0 to 5 of the top curve, which is 9 minus x, minus the bottom curve, which is x squared minus 6x plus 9 with respect to x, right? So top minus bottom. So this is going to be a 9 minus x minus an x squared plus a 6x minus a 9, which I'm going to clean up before I integrate because it'll make my life a lot easier. So this is a 0 to 5 of a negative x squared, a plus 5x, and the 9s go away. So I get that this is negative x cubed over 3 plus 5 halves x squared, evaluated from 0 to 5. When I plug in, that's going to be a negative 125 over 3 plus a 125 over 2 minus a bunch of 0. So if I, honestly, you don't have to do this, but I'm going to argue the fastest way to do this problem is to factor out a GCF of 125. If you factor out a 125, you're going to get that this is a negative third plus a half, which are pretty easy fractions to add. So I'm going to get that this is a 125, right? And then I'm going to make these 6. So this is a negative 2/6 plus a 3/6. So I get this is a $1.25 times a 1/6, or 125 over 6, right? So that's what that area should be. Now I can also confirm that if I want in a calculator, right? If I want to confirm that in a calculator, it said a non-calculator problem, but that doesn't mean you shouldn't check your work in a calculator. That's just a good idea. So I'm going to put my y1 in as x squared minus 6x plus 9. I'm going to put my y2 in as 9 minus x, right? So now what I'm going to do, right, is I'm going to do math 9 So math 9. And I want to integrate top curve minus bottom curve, but I always label my curves in the order I can see them. So that's y2 minus y1. So I'm going to do my variables are going to be y-vars function y2 minus vars over to y-vars function y1, right? So to g minus f, right? With respect to x from 0 to 5. And there we have it, right? And if I math frac it, what did I do wrong that we get a 215 over 6? Oh, sorry. Did something stupid. It's not a 215. So one of the many reasons to check. So let's go back, hit enter. Now we math frac. My bad. There it is, 125 over 6 it is. All right, cool. It was an odd thing that it happened to just be the reverse of the numbers, but that happens. So that's one of the reasons we check when we enter stuff on a calculator. All right, so for P1, again, we're finding the area between two curves, f and g, on the interval from 0 to 2. So a point to make about E1. So in E1, it happened that the curves intersect. It is worth determining if the curves intersect, but if it doesn't naturally happen that you can find the intersection really quickly, it's kind of worth ignoring. So the reason I mention that is because these two don't intersect. So if I were to look and see if these intersect, right, they're not going to. So I can check if x squared plus 2 equals 2x minus 1. I'd get x squared minus 2x plus 3 equals 0, and this doesn't factor because the 1 and 3 would have to have the same sign. So not only is this prime, which pretty much means that, so suddenly this is not worth my time, right? Because if this is a non-calculator problem, which it is, then the numbers I'm going to get are going to be fairly nice numbers, and if I don't get nice numbers, like if I'm not getting numbers that factor, this isn't worth my time. So I don't really care. So instead, if they don't intersect, what that means is that one of these curves is on top of the curve the whole time, and the other one's on top, or is on the bottom. One of the curves is the top curve, and one of these curves is the bottom curve. So if we were to just look really quickly at the easy points from 0 to 2, we can figure out pretty quickly what these graphs look like. So you don't have to do like a really fancy graph, right? But it's kind of worth knowing what this looks like, right? So let's start with the x squared, right? So x squared plus 2 is a parabola that has its bottom at 0, 2. Right? And if you plugged in 1, you'd get 1 squared plus 2, which is 3. And if you plugged in 2, you'd get 4 plus 2, which is 6. And I didn't quite give myself enough space for it, but it's up here. Right? So we're looking at a graph that looks kind of like this. And again, it doesn't have to be a beautiful graph. That's kind of my parabola. Close enough. 2x minus 1 is going to have a y-intercept of -1, and then it's going to have a slope of up to right 1, up to right 1. And what you'll see is that at no point, if we draw this curve, at no point in the interval that we're given do the curves flip-flop. So the interval I'm looking at is basically this shape, meaning that f is always on top and g is always on the bottom. So when I integrate, the area that I want to find is going to be the integral from 0 to 2 of the top curve, which is x squared plus 2, minus the bottom curve, which was a 2x minus 1, with respect to x. So I'm going to clean that up and integrate. So what will happen here, right, is we're going to get that this is an x squared. The 2 is positive. This is going to become a minus 2x and a plus 1. So that plus 2 and the plus 1 would give me a 3. That means I'm going to get that this area is an x cubed over 3 minus an x squared plus a 3x evaluated from 0 to 2. Right, so that's 8/3 minus 4 plus 6. And then minus a bunch of zeros because when I plug in 0 to all of these, they all come out to be 0. So I'm going to get an 8/3 plus a 2, which is 8/3 plus 6/3, or 14/3. And we can check that on a calculator. So when I check it on a calculator, I can either put this in as y1 and y2, right? Or I can actually type the whole thing. I'm going to argue it's worth putting them in as y1 and y2, especially because on an actual AP test, there's a good chance that you would have multiple prompts related to the same functions. So again, I'm just going to check this on a calculator. We'll quit out. We're going to go ahead and do math 9, right? And then we want to do the thing I called y1, right? And that's the thing I called y2. So we're going to do vars function y-vars. And we'll pick y1 minus y2, because in this case, my f is on top of my g, comma, with respect to x from 0 to 2. And then we go ahead and hit math frac, and we should get our 14/3, right? So you should check these on a calculator even when they're non-calculator problems, because that's how we build the calculator skills so that when we have a calculator problem, we can do the math. So if the bounds aren't given, you're going to need to find the points of intersection. So it turns out, if we look back at E1, that the bounds that I gave you happen to also be the points of intersection, right? And that's convenient, but it's not always true, as we saw in P1, right? We saw that the bounds I gave you were not points of intersection. So if the bounds aren't given, we're going to have to find the points of intersection, meaning find where the two curves intersect, and use those bounds. Keep in mind that if you're using a calculator, you shouldn't round or truncate those values until after you use them, because that would alter your final answer. We never round or truncate a number that we're still using. We only round or truncate final answers. So we're going to go ahead and do E2 in a calculator, right? So conveniently here, I did you the solid of showing you which color's which. This is clearly F, this is clearly G, because they're color-coded in my graph. So the trick is I need to find this point A, and I need to find this point B. I need to get those numbers, and then I need to integrate, right? So I'm gonna go ahead and call that A and call that B, right? When I put the two functions in my calculator, and this is a calculator required question, so I'm going to get sine, obviously make sure you're in radian mode. I haven't checked in a while because I haven't been doing degrees in pre-calc, but if you're in, for instance, a physics class, there's a good chance that you switch back and forth to degree and radian mode regularly in my class and also that class. So just be mindful that if you're in degree mode, it's really going to wreck your entire AP calculus experience on that test. All right, so I double check that everything's right? You should double and triple check, because if it's wrong, it's going to wreck everything. And I'm going to go ahead and graph, and I can see what it should look like because I gave you the graph, right? So there's my graph, and this is the window we're talking about, right? So what I need to do is I need to find the points of intersection. So this is the one I called A. I'm going to go ahead and second calc intersect, which is 5. And I'm going to scroll to right about where they're hitting each other, right? And then hit enter for the first curve, enter for the second curve, and enter for the guess. Now that x value, so I'm going to take a little screenshot just so that we can reference it, right? But that first x value, right? That first x value that I got, that's A, right? But we don't want, we're not going to have the opportunity to take a screenshot and use it that way. So what we're going to do is we're going to quit out, right? On the AP, you need to be able to use that number again. So if you hit x now, this x that is the intersection, that's currently stored as x. That'll stay stored as x until something overwrites it. So while it's here, I'm going to go ahead and store this as alpha A, and I'm going to call it A. So I'm going to go ahead and say, let's call A approximately 0.853468836, ... right? I'm then going to go back to my graph, and I'm going to second calc intersect again. So I'm going to scroll to where I think the second intersection is. And again, you just have to be close. The calculator will do all the heavy lifting. So I'm close, first curve, second curve, enter, there's my other intersection, right? And so now my calculator has overwritten this value, and this is the new x value, right? So if I now quit out of this, so second quit, and I hit x, it's going to have overwritten, and that's going to be the value. So I'm going to store that as alpha b. So I'm going to make a note that that's my a and my b. So I'm going to go ahead and say, cool, we're going to call b 7.390377464, and that's going to keep going, right? So those are my values, right? What I now need to do is, now that those are stored, right, I need to write what the area is going to be. So the area, and I have to write this in calculus notation, I can't use the calculator, right, is going to be with the thing I called A, which I clearly label for the AP. I need to either label it or I need to write all of those digits out, and I would much rather label it. To B, the thing that I called B, I have to label it, or I have to write every single digit up here, which is no fun, right? You cannot round or truncate until the final answer. And then because the AP, or in this case, I called them F and G, you can call them F and G. So I would do f of x minus g of x. If they had not called them f and g, if they had just called this one y and this one also y, you can't play the game. You can't call them y1 and y2. You would physically have to write out the entire equation. But conveniently in this problem, because I labeled them as different function names, you can use the function names. This is what I write, and then this is what the AP wants. At no point do I write math 9 or function integrate or y1 minus y2. That's just not a thing. The AP is not okay with that. So I can't use calculator notation, and the only reason I can use this A and B here is because I labeled those letters rather than having to write out all of the digits, and that's totally okay. So what I'm doing on my calculator is hitting math 9, right? And what I want to integrate is y1, because that's the one because remember, I always do them in the order they appear, because then you can't get confused and you don't have to keep going back and checking. So I'm going to do y1 minus y2, so vars over to function y2, comma, with respect to x, from, and then the lower bound is alpha a, and the upper bound is alpha b, because again, had you not stored these, you would physically have to type that entire number, and you're going to hate your life. And I hit enter, and there's my answer. So my answer is 5.626, and that's where I can round or truncate, and I'm done. that's where I go to 3 places. For anything before my final answer, I need the entire value. And if you were asked to use this final answer again, let's say this is the final answer in the first part of a multi-part prompt, if you had to use this answer for some other part of the prompt, you should use a stored answer, not a rounded or truncated answer. Anytime you're using an existing answer to do something else, you should make sure you're not using a rounded or truncated value. All right, so you're going to go ahead and try this in for P2, right? So this is the area that we're talking about, right? The area bound between the two curves. So go ahead and give it a try. Again, this is definitely a calculator question. You're not doing this by hand. Pause me if you don't want me to do it. So g of x is the black curve. It's definitely the top one. F is the bottom. Again, that's convenient because I color-coded them. It's not always going to be color-coded. Sometimes you're going to have to like logic your way through and figure out which one of these is a cosine. And you can tell that this is the cosine because it goes up and down and up and down. You can tell that this is the one that's an x squared because it's just a parabola. So you could figure that out, but that's where we're at. So I'm going to go back to my y equals, right? And I'm going to go ahead and put in negative cosine of 0.2 x squared. Close that and then plus 1, right? Double and triple check that you put the right value in, right? And a negative 0.1 times the quantity x minus 1 quantity squared plus, I think that's a 0.3x, but I'm going to move the calculator to double check, so 0.3x. So again, double and triple check that you put this in correctly because you're going to be miserable if you don't. And then graph, and it should look like this. Now this is tinier than, like this looks really small, and that's probably because I need to zoom in, because if you look at the scale on the graph that I've given you here, it's definitely smaller than that. Okay, so there's the window we're talking about. Yet again, I'm going to second calc intersect. So I'm going to do second calc intersect, which is 5, and I always work left to right. You don't have to do that, but it seems like they intersect somewhere around here. Okay, so there's my first answer, right? And I'm going to go ahead and notice that that y value actually is 0. It doesn't quite look like 0, but it is. So this value right here, right, I'm going to call that A, and I'm going to say it's approximately 0.2087951, right? This actually is 0 because that would be moving the place 5, 1, 2, 3, 4, 5. It would be a decimal point with a lot of zeros before that 3. So that's actually 0. I'm going to do it again, right? I'm going to go ahead and do second calc intersect. And I'm going to go to the other point of intersection. And really all you have to do when there's only 2 points of intersection is just get physically closer to this one than you are to the other one. And that's pretty much all you need. So enter, enter, enter. And there we have it, right? So that's my other point of intersection. Drag that guy over here, right? So that's the one I'm going to call B, which is right here, right? So my B is approximately 2.3151063, right? And I'm going to store those. So I did do something silly, so I'm going to have to go back and fix it because it's a thing I tell you to do and then I forgot to do it. Unfortunately, I forgot to store this before I changed it. So I'm going to have to go back and second calc intersect again, but rather than go and delete this in this video, I want to prove the point to you that sometimes you make that mistake and then you're grumpy about it. So I'm going to store this as alpha b, right? Oh, my bad. Alpha b, there we go. All right. Cool. And then I'm going to have to go back to my graph and second calc intersect again because, again, I screwed up and accidentally didn't store... I didn't store that first value while it was still x, and so you don't want to store a rounded or truncated value. You want to store the whole thing. So there it is. Now I quit out, and now it's still my x, and I can store it as alpha a, right? So we're going to do store as alpha a, and now I'm good. So this is now a, and this is now b. Now what I want to do, remember, it's my job to communicate understanding, so I have to communicate what the integral is, right? I need to say that that this is the integral from the thing I called a to the thing I called b of g of x minus f of x. And again, had I not labeled, like these functions are not handed to me as f and g, I need to write out the entire equation for each function. But because they were labeled as specific functions, I can use the notation that was handed to me, which is great. So I'm going to go ahead and do math 9. Right, now in this case, notice that this is my y2 because I always put them in the order that they're given to me. So this is not y1 minus y2, this is y2 minus y1, and you have to pay attention. So I'm going to do y2 minus my y1, comma, with respect to x, from alpha a to alpha b. And hit enter, and there's my answer. So my answer is approximately 0.452 or 3, depending on if you round or truncate. So again, the AP needs to see these values. It needs to see this integrand, which is not in calculator notation. It needs to see this answer. All right, cool. All right, moving on. So we're gonna do a quick challenge problem. There aren't 2 of these, it's just 1, but I wanna walk you through some logic. So The graph below consists of the function y equals negative x squared plus 6x. So that's this one because that's definitely a parabola. So this is y equals negative x squared plus 6x, right? And a line that is negative 3x plus 18, right? Find the area of the shaded region. So we want to find the area of this shaded region. Now we're going to learn another way to do this in 8.5, but for right now, unfortunately, in order to find the area of the shaded region, you basically have to treat it as two separate regions. You have to find the area of region H, find the area of region K, and recognize that the shaded region is the sum of them. So if I want to find the area of region H, we can see that this bound is 0 and this bound is 3. So the area for region H is going to be the integral from 0 to 3 of negative x squared plus 6x dx, right? So that's going to be a negative x cubed over 3 plus a 3x squared evaluated from 0 to 3, right? So the area for H is going to be a negative 27 thirds plus 27 minus a bunch of 0, which seems to be a negative 9 plus 27 or an 18. So area H is 18. Then I'd need to find area K, which is from 3 to 6. Now, honestly, you can find area K in one of two ways. If I were going to find area K is a triangle. So you could find area K by integrating, right? So you have two options. You could either do calculus, where you integrate from 3 to 6 of this negative 3x plus 18 dx, and that's right. Or you could recognize, oh, hey, convenient geometric figure, you are a triangle with a base of 3 units and a height of 9 units. So this area is 1/2 3 times 9, right? So I'm going to get that this is 27 halves. Or if you prefer, you could get that this is 13.5, right? Either of those would be fine. If you integrate with calculus, you're still going to get the same 13.5, right? If you use calculus, you'd get that this is a negative 3/2 x squared plus 18x evaluated from 3 to 6, and you'd be kind of miserable plugging in some of these numbers, but I assure you that after you plug in the numbers, you get the same value. That means that the area of this whole thing, right, the area of the shaded region is 18 plus that 13.5, so it's a 31.5. Great. And again, you could totally use calculus to find the area of K. It just happens that K is a triangle, so in this situation, it's easier not to do that. The trick here, though, is that in this case, we are doing top minus bottom, but the top is this curve and the bottom is the x-axis, right? And in the second interval, in K, the top is this curve and the bottom is this axis. The two curves are not top minus bottom related to each other because on the interval from 0 to 3, there's only the parabola, and on the interval from 3 to 6, there's only the line. So just wanted to show you an interesting challenge problem, and that's the end of this video.